My name is Mariano Zeron, and in this video, we're going to see how we extend Motex objects from one dimension to higher dimensions. So far, in pretty much all the videos that we've been doing, the results that we've been quoting are quoted for one-dimensional functions, but that's partly just for ease of exposition. Every time that we want to present an example, every time that we want to present some code, it's easy to do or deal with one-dimensional objects rather than high-dimensional objects. But in this video, what we want to do is identifying what constitutes a one-dimensional object. We want to extend it to higher dimensions. And what we have is that high-dimensional objects will have the same results or will satisfy the same results that one-dimensional objects satisfy. But first, let me give you some historical context. So much of Chebyshev approximation theory has existed for more than 100 years. But for most of this time, the theory has existed for only one-dimensional objects. And it's been in recent years that we've had extensions to higher dimensions. In this video, we're going to focus on the extension that has been done for the Motex library, the one that you can download and use. And we'll also compare it to a couple of other extensions to higher dimensions that we found particularly interesting. So let's start by, once again, identifying what constitutes a one-dimensional object. So you probably already have seen this many times, but it's important that we have a starting point with a one-dimensional object, because I want to identify how we extend every single bit of what constitutes a Motex object in one dimension. So again, we've got a function, let's say this is f, and it's a one-dimensional function. What do we need in order to come up with a Motex object? We mainly need three things. First of all, it's a domain of approximation, which is an interval. Second are the Chebyshev points on this interval. And third are the values of the function on those Chebyshev points. And once you have all these three things, we can come up with an object, Pn of x, that, as we already know, can be expressed in different ways. One of the ways in which we express it is in terms of Chebyshev polynomials. We can equally express it as a linear combination of Lagrange polynomials, and we use the barycentric interpolation formula to very efficiently and stably evaluate this object. So that is essentially what we have in one dimension. The question is, how do we extend this to high dimensions? So let's start with the first part, which is the domain. So the natural extension of an interval in one dimension to high dimensions is a hyperrectangle. Let's take a look at a two-dimensional rectangle. And I'm going to stick to a two-dimensional case because once you understand how things work for Motex objects in two dimensions, you'll be able to understand how it works in high dimensions. So let's take a look at an example that we would have in higher dimensions. So take, for example, this is our x-axis, this is our y-axis, this is our z-axis here. And let's assume that we've got a surface that we want to approximate. So we've got this surface over here. And the domain where we want to approximate it is a rectangle, which is going to look something like this. Take a look at, just notice that a rectangle is the result of taking the Cartesian product of two intervals. So for example, if we had an interval over here, and we had an interval over here, this thing, which is going to be the domain, is just a Cartesian product between the two. Naturally, if you want to extend that notion to high dimensions, let's say 3 dimensions, we would have another interval with which you can take the Cartesian product, and then you've got a hyperrectangle. So those are going to be the domains of approximation. So that's the first thing. Now let me change the view of this domain so that we see it from above, because it's going to be way easier to understand what goes on with the Motex object in higher dimensions. So we've got our domain here, which is the rectangle that I mentioned before. Let me just draw the x-axis a bit better. That's the x-axis, that's the y-axis. And we've got our interval here. We've got the other interval over here. So what is the next thing that we need? Those are the Chebyshev points. That's the next step. So we already know that if you've got an interval, such as this, for example, Chebyshev points are already completely determined. You just have to choose the number of Chebyshev points that you want. So immediately we can come up with a grid of Chebyshev points over here. like this. And for that interval, you can define once again a collection of Chebyshev points. It doesn't have to be the same number as the ones that we've got here. Let's say that we only choose 3 points over here. Now, just as we did with the domain, taking the Cartesian product of 2 intervals, if we take Chebyshev points along which are within this interval and the Chebyshev points which are along that interval, we can take the Cartesian product once again. And what we end up with is a regular mesh of Chebyshev points, in this case for 2 dimensions. So we would end up with something like this over here. And that is basically, or that is essentially the basic mesh that we're going to work with. So notice that this mesh is a regular mesh. And just as we can build Chebyshev objects using this regular mesh, you'll see in a second that we can use irregular meshes in order to build Chebyshev objects, which gives you a bit of an edge and can, in some cases, make the computation or the building of a Chebyshev object much more efficient. So that was the second step. Notice, of course, that for high dimensions, you would do the same thing as we did for 2 dimensions. We would have, let's say in 3 dimensions, 3 collection of Chebyshev points. You take the Cartesian product of all of them, and you end up with a 3-dimensional mesh of Chebyshev points. Next step, we need the values of the function on Chebyshev points. So that's what you do. You just compute, or call the function on these points, get a collection of values, and now you've got the 3 basic ingredients that you need in order to come up with a Chebyshev object. The question is, what does that object look like? And this is where most of the extensions to high dimensions differ a bit. We're going to focus on the extension that is implemented within the Motex library, but we also want to mention a couple of other extensions that have come up recently which we find interesting. So on the one hand, we've got the extension that you have available within the Motex library. So we're going to refer to that extension just by M for Motex. But there's another 2 extensions. One of them is by Professor Trefethen and his group of collaborators, students, postdocs, and so on. We've got a wealth of publications in this area, and we've got some really clever algorithms, but some restrictions that we'll talk about in a second. And the final one is the one that was published quite recently by Catherine Glau and her collaborators that also has some interesting properties. But now let's go back to our main focus, which is the Motex extension. And we already have the domain of approximation, which is this one here. It has a mesh, in this particular case, a regular mesh of Chebyshev points. And we take or evaluate the function f, which in this case is 2-dimensional, on those Chebyshev points. So we've got the 3 main ingredients. Now the question is, how do we put that together into a high-dimensional object? Notice that this line over here, if you take a cross-section in this direction, the function, what you have here is a 1-dimensional object. Because at the end of the day, you've got these Chebyshev points on this 1-dimensional interval, and you've got values associated to those points. So that constitutes a 1-dimensional object. In the same way, you can do that for this cross-section over here, and for that cross-section over here. So in principle, if you're interested in evaluating a point, let's say here, let's put it as a round dot, you wouldn't have a problem, right? Because you would identify, or you would use this 1-dimensional object, you evaluate that point, and that gives you a corresponding value. That's fine. The question is, what happens when you want to evaluate, let's say, a point over here? But notice that that point has corresponding points over here, and over here. And you can use these 1-dimensional objects in order to come up with an approximation for the value of the function on these points. Once you have that, what you have are values here, here, and here, which correspond along this dimension to Chebyshev points. So it's, once again, what you have in essence is a 1-dimensional object that you can form, or that gets built, by considering the Chebyshev points along that dimension and the corresponding values that you just calculated on them. So you can call once again the barocentric interpolation formula to get an estimate of the value of the function on that point. And this is the way that we evaluate the high-dimensional objects in Motex. Essentially, the high-dimensional Motex object, it's a collection of 1-dimensional objects. So essentially what we're relying on is the power of the one-dimensional objects to extend all the results that we have for one dimension to higher dimensions. Let's take a look, for example, at the accuracy. The accuracy that we have at each of these points is the accuracy that we know we have for one-dimensional objects. That is, as you increase the number of Chebyshev points along that dimension, the error at these points gets reduced exponentially. So you've got really good control over that. And that's one source of error for the final evaluation of this two-dimensional object. What happens in the next step? Once you've reduced the problem from a two-dimensional problem to essentially a one-dimensional problem, and I say this because once you've evaluated values here, you end up with this one-dimensional object. So we've reduced the problem from 2 to 1 dimension. Now what we have is the evaluation once more of a one-dimensional object that will introduce another source of error. But again, that's controlled by the way that one-dimensional objects control error, which is they converge exponentially as you increase the number of Chebyshev points, which in this case lie in that direction. So by increasing the number of Chebyshev points along each of the dimensions, in this case would be along that direction and along that direction, you have control over all the sources of error in your approximation. And in this way, you've got a way of controlling the error for the whole high-dimensional object. In the same way, look at the fact that each of these one-dimensional objects are independent from one another. So in principle, I could have built this one-dimensional object with more Chebyshev points. So I could have introduced here more granularity, which you do, for example, when you want to get a high degree of accuracy, or when the function is a bit more difficult to approximate. However, doing that doesn't impose the condition that you would have to do it, let's say, on these other two. This is the way that the Motex library introduces flexibility within the mesh. So we started off by saying that we can use regular meshes, and that is the case. But by noticing this, you can introduce a regularity in the mesh, giving you extra saving times, because if you wanted to achieve a certain degree of accuracy, overall accuracy, in your approximation, and that meant increasing the number of Chebyshev points on this part of the function, you don't have to do it on the top part of the function. If you were restricted to regular meshes, you would have to do it. In this case, you don't. And so you save quite a bit of time in the building part of the process. Also notice that we can harness the power that one-dimensional objects have of computing or approximating the derivatives of the original function they want to approximate. So what we can do is, by taking the derivatives of, let's say, these objects along that dimension, you can come up with an approximation for the partial derivative of the function along that direction. If you wanted to do it in that direction, you would do the same, but considering Motex objects in that direction. If you want to take the cross derivative, for example, you can compute the one-dimensional objects that you got in that direction. You can compute their derivatives with respect to that direction, followed by the derivative of the Motex objects that you build as a result of evaluating these ones, but along that direction. And that gives you the cross derivative. And again, given the way that the object is built, all the nice properties that we have for the approximation of derivatives for one-dimensional functions extend to high-dimensional functions. So you may have noticed that from a methodology point of view, there's something we still need to mention. And that is, when you're about to evaluate the value of this one-dimensional Chebyshev point, the one that runs vertically in this example, when you're evaluating it on this point, it relies on these values, that one, and that one. But these ones have been calculated by evaluating one-dimensional Chebyshev objects, these ones here. So these ones are not the exact value of the function. So there's an error there. And the question is, how does that error propagate to the final result that we obtain here? So we're going to take a look at that. We'll give you an idea of what's going on. So at the end of the day, what we want to evaluate is, or let's say the final value that one obtains at this point is obtained by evaluating a one-dimensional object. So that's what we're going to start off with. The one-dimensional object that, as we know, has that expression here. And we're going to take the sum, let's say that the object has endpoints, and that's going to be evaluated at some value, let's say f twiddle. These are the f twiddles over here. That one there, that one there, and that one there. And these are Lagrange polynomials. And what we want to see is how that behaves with respect to the two-dimensional function f of x comma y. We want to see exactly what happens with this expression, because this is the expression that controls the error of the approximation. Now, notice that these fi twiddles are actually fi plus an error, where fi is the actual value of the function on those points. So essentially, this is going to be equal to, I'm going to remove this picture as well. It's going to be equal to the sum of the fi's plus some error that you have at that particular point that we're going to denote by epsilon I. You're going to have here Lagrange polynomials minus f of x comma y. And the important thing to notice is that we can regroup, and this is going to be very important because it's going to isolate the different sources of error. You can regroup this expression so that we get f of I times Li of x minus f of x comma y plus another sum that is going to have only the errors here. Epsilon I Li of x. And of course, using a triangle inequality, what we have is the following thing. I'm going to be skipping, I'm not going to justify the whole, all the steps, but basically I'm taking a uniform error that I can factor out that bounds every single one of the errors. And what we have here is this thing, this expression over here. Notice the following thing. These fi's are the actual values of the function. So essentially, it's as if we had evaluated the function on these points. And then using the Chebyshev object that results from doing so, which is just a one-dimensional object, the way that we've known it so far, we approximated that value over here. And this error is the error that you would have from that one-dimensional object, but by getting the actual value of a function. And we know that that is controlled because it's a one-dimensional object, and that is going to tend to zero exponentially as the number of Chebyshev points along this dimension, along this axis, as they increase, this tends to zero exponentially. Okay, so that's going to be one source of error. The error for the two-dimensional case running in that direction. But we've got another source of error, which is the error that you get in that direction when you evaluated these points over here. And that's the one which is controlled by this epsilon over here. The important thing is that as you increase the number of points along this axis, the error for that object, and for that object also decreases exponentially. So as a result, what you get is this one here decreasing exponentially. This one controlled by the number of Chebyshev points along this axis. That one here controlled by the number of Chebyshev points along this axis. So when you increase both of them, you get this expression overall goes down to zero very quickly, which is what we wanted to have. So this has to do with the approximation capabilities that are the extension that is offered through the Motex library has. But now let's take a look at some of the interesting aspects that other extensions that we've come across have. As I said, one of the things, or the things that really distinguishes all the extensions that we know of, is how you come up with an object that you can evaluate. Notice that we rely in the Motex library. It heavily relies on having one-dimensional objects. That's in some way that's the sort of the atomic particle of the whole object. And given the way that it's put together, the extension has all the nice properties that we wanted to have. Also because the evaluation at the end of the day relies on applying the barycentric interpolation formula several times, and we know what the nice properties of this evaluator has. So perfect in that sense. Take a look, for example, at the algorithms that this methodology, the one that headed, let's say, by Professor Chebyshev. So one of the things they do when they want to evaluate a point in this domain, for example, of course, what they've done is once they have a regular mesh of Chebyshev points, They've evaluated the function on those points, they've got that information, and what they do is the following thing. If they want to evaluate a point around here, in a very clever way, what they do is identify the areas where the approximation that they have so far has the maximum error. And if it's, let's say, around that point, what they do is take a cross in that direction, a cross section in that direction, and a cross section in that direction. What they have there, again, are two one-dimensional objects, one running that way, the other one running that way. With those two, they come up with a two-dimensional function just by simply taking the tensor products of them. And they add that to the approximator that they have so far. Once they recalculate what the error is, they focus on the area where you have the maximum error and carry out, let's say now here, and once again carry out this same procedure. As a result, one of the things that they obtain is that they got phenomenal accuracy with the object that they generate. However, this comes at the expense of having to evaluate the function many, many times, because also another thing that they do is once they've identified that point, and they draw across here and across here, they introduce a huge degree of granularity with these objects, meaning that they introduce many Chebyshev points along that direction. And same here. Unfortunately, for the applications that we're interested in, which are approximating pricing functions, in particular for the calculation of risk metrics, that is of no good to us. Simply because at the end of the day, to build one of these objects, you would end up evaluating the function many more times than you would like to. So unfortunately, that methodology, despite all the clever algorithms that it uses, which, by the way, you may find very interesting, so you should take a look at them. You'll see at some point in the video the references that we make to some of his papers. Despite that, despite all the clever things that they do, it turns out to be not as good as the Motex implementation that we have for the particular context that we're interested in. Also, something else is that the extensions they've made are for 2 and 3 dimensions. Nothing more that we know of. So again, is limited by the extension, the dimensionality of the extension they have. The other extension that we've mentioned is that by Glau and her collaborators. So they restrict themselves to regular meshes, first of all. They have extended it to all dimensions, which is good. But in order to come up with the object, once they've evaluated the function on the regular mesh, they rely on evaluating or running the fast Fourier transform many, many times. Especially on higher dimensions, that becomes a bit of a problem, because then the building phase becomes more expensive than we would like to. So that's definitely a drawback that it has. So, summarizing the main properties of the Motex methodology. The first one is that the extension that we've presented is valid for any dimensionality. I might have not made it completely clear when I was explaining the two-dimensional case, but the way that we put together the one-dimensional objects and the way that we evaluate them to come up with an evaluation for the two-dimensional objects is essentially the same for any other dimensionality. In 2 dimensions, what we did is all the one-dimensional objects are evaluated, and then the result gives you a one-dimensional problem that then you evaluate. In 3 dimensions, you would go from 3 dimensions down to 2 dimensions, and then from 2 dimensions down to 1 to then finally evaluate the result. We've got extension to any dimensionality. The second one is that we've got phenomenal convergence properties that we presented here, which rely on the exponential convergence that you've got from each of the dimensions that need to be iteratively evaluated. So you would have a source of error, let's say from 2 to 1, and then from 1 to the final results, you have another source of error, which would be these 2. But each of them are controlled, precisely because of the result that we have in one-dimensional theory. The third property is the flexibility that you have with a mesh that you define your object with. So if you need to be more accurate in certain parts of the domain, let's say down here below, you increase the granularity, achieving those degrees of accuracy that you need for that area. But you don't have to do that at the expense of increasing the granularity at the top, which you would have to do if the mesh had to be regular. And the impact that this has is that on the building phase of the whole process, when you're building the Chebyshev objects, you can be much more efficient. The fourth property, the evaluation of the Chebyshev object in high dimensions relies on the evaluation of Chebyshev objects of one dimension, which uses the barycentric interpolation formula. And the barycentric interpolation formula has great properties, really good speed, and numerical stability. And these carry through to the extension in high dimensions. Fifth property has to do with derivatives. So one-dimensional objects can approximate the derivatives of the function they're evaluating, or they're approximating. Given that we have this characteristic for one-dimensional objects, that can be extended to high-dimensional objects, meaning that given a function of high dimensions, with a single Motex object for that function, we can approximate not only the function itself, but also its partial derivatives. That is, when it comes to pricing functions, we can approximate the Greeks. And the final property, the sixth property, has to do with the implementation of all this methodology. If somebody is interested in implementing this, coding it up from scratch, it can be done really, really easily. Once you've got the implementation done for one dimension, which is very straightforward, that can be then put together into blocks so that you can go, let's say if you choose 5 dimensions for a particular object, then the same function that would evaluate that object is the same function that would evaluate a 3-dimensional object, because at the end of the day, it's just an iteration. We go from one dimension, you reduce it down to the one below, and then you reduce it down to the one below, and so on, until you exhaust all the dimensions, and you get the final value. So that's also another important aspect of the methodology. Other extensions that exist, for example, these are the two that we've been mentioning, also have some interesting properties. We definitely encourage you to go and check the literature that we will be putting on screen. Some of the algorithms are actually quite interesting, but they have some weaknesses for the particular application that we're interested in. At the end of the day, we believe that the balance that each of these properties bring to the whole setting is what makes the Motex methodology very strong and optimal in the application that we're interested in, which is approximating pricing functions within the computation of risk metrics. Thank you very much for being with us in this video. Please get in contact with us on the email that appears on screen. Thank you very much.